All right. So now I want to take a concrete example and work out and use Stokes' theorem or some theorem at all. Let's see which one applies. So I'm going to start with a vector field f, which is equal to 2z, comma 3x, comma 5y. And my surface S is going to be a parabola z is equal to 4 minus x squared minus y squared, as well as z is going to be positive or non-negative. All right. And C is my curve that bounds this vector field S. This is surface S. All right, so my surface S looks like this. Like this. There is my curve C bounding it right here. Pretty nice. S and the curve C. So now if I want to find the work, I want to find the work F dr over this closed curve C. And what I could do if I wanted to, I could, since this curve is bounding a surface S, I could just as well use Stokes' theorem, which is what I want to do right now. I want to use Stokes' theorem here. So this gives me the double integral over the curl of F dot n ds over the surface S. Let's see. What I get here, the surface S is given by z is equal to 4 minus x squared minus y squared, so I can find out the n and the ds. So the n is the minus 2y, the fx minus the fx is minus, so this is minus the fx number, minus fi and 1. So in my case, the normal vector would be the fx over f, the x derivative of f is 2x, 2y, and 1. I have to also find the curl of f, so let's find that. Let's take I, j, k as usual, put the dx here, the dy, and the dz, and put my vector field down here, the 2z, 3x, 5y, which gives me the first component is the first column deleted, which gives me the dy of the 5y, which is a 5, dz over 3x, which is 0. The second component gives me dx over the 5y, which is 0, as well as the dz over the 2z, which is a 2, and the last component, it gives me minus 2, but there's an extra minus sign for the second component, so it gives me plus 2 here. And the last component is the x derivative of 3x, which is 3, minus the y derivative of 2z, which is nothing. All right. So now I can write down what, so I have this n, I have the vector field f. So I figure out what this integration comes out to be. This integral comes out to be double integral over the surface S, which I write down in a second, but this works out to be the fx, the m. This is my m, my n, my p of my vector field. This comes out to be 2x times 5 plus 2y times 2 plus 1 times 3 dA over the circle. Radius 2. This is the circle radius 2 here. C, the curve C. I'm sorry, over the disk here. This is the disk, of course, not the circle. I have the whole disk. Radius 2. So this is my integration domain here in R2. This one here, the disk. Okay, so let's go about this. Now, of course, since it's a disk, I'm going to use polar coordinates here, of course. So that means that the x and the y are r cosine t times r sine t respectively. So that this whole integration comes out to be the double integral of 10x, but x is equal to 10 times r cosine of t, or theta, whatever you want, plus 2y plus 4y, but y is equal to r times sine of t, plus 3. The dA turns out, of course, to be the r d theta, r dt in this case. And the angle t goes from 0 to 2 pi to cover the disk of radius 2. And the radius goes from 0 to 2. So that's it. It's an easy integration. I can use Wolfram alpha to work this out, and if I use the Wolfram alpha to work this out, I get 12 pi. 12 pi, which incidentally is also what we got when we worked this out in class, using the old-fashioned way of working this out, namely using the parameterization of this circle here straight out as a cosine t, sine t, and a 0 for the z. Then I can work this out directly. So in this case, it turns out that Stokes' theorem does not help too much here, doesn't make it that much easier, but it's a different way to work this out. So if I wanted to use it, I could use it just fine. A matter of taste in this case. But as it usually turns out, you can see that the curl of the vector field is always simpler than the vector field itself. This is the vector field itself, 2x, 3x, 2z, 3x, 5y. The curl of it came out to be 5, 2, 3, constant in other words, which made the integration fairly simple. Alright, very good. So there's one example of working out the flux integration, of using the flux integral to find the work according to Stokes' theorem. Good.